Yeah, exactly. All right, well, without further ado, I'd like to introduce a flow battery team looking at storage for the grid.
Good afternoon, everyone. My name is Mason. With me here today are Maria, Peifu, and Christopher, and we are the Hydrogen-Bromine flow battery team. I'd like to start, I think we've heard a lot today about the different increasing adoption of renewable technologies onto the utility grid. And this is something that's happening here in the U.S. for a variety of reasons. Certainly the carbon abatement issue is something that we're all aware of. I think additionally there are issues of energy independence as well as national security at stake here. And all of these are good motivating factors to adopt an increasing amount of renewables onto the grid. Now, against that backdrop, there are some technical challenges that we face as we see more and more renewables coming online. And fundamentally, this has to do with the variability that's inherent in renewables. We don't have the same type of control over wind and solar as we do over other types of electricity generation. The sun shines when the sun shines, the wind blows when the wind blows, and we've got to try and find a way to make that work for consumers that demand electricity when they demand electricity. What I've got here is a chart that shows just a couple of days from the Bonneville Power Administration looking at consumer demand versus wind generation. And I think there are really a couple of things that pop off of this immediately. The first one is if you look at the long time scales over several days and just map the wind generation against the load, they just don't quite fit. There's some issue of needing to shift electrons around to better fit when people most need the electricity. I think as you zoom in to the circle on this as well, you see that there are shorter time scales where you've got massive changes in power in very short amounts of time. And this is an issue for grid stability and reliability. And both of these things are just inherent in renewables. And this really motivates the need for electricity storage, such as the flow battery that we're going to go into and describe more here. One thing that I do want to make sure that everyone remembers and bears in mind is that storage is nothing new. This has been around for a long time. We've been building dams for many, many years, and this is just a new way to look at creating this type of flexibility in the grid. Now, the technology that we're working on, that our research team at LBNL is working on, is a hydrogen-bromine flow battery. What's unique about a flow battery is that there's an ability to independently scale the energy and the power. And I think we've heard a lot about this. We've got an intelligent group here, but just to make sure that we're all on the same page and clarifying, the difference between energy and power is something that can really be illuminated with a flashlight. If you think about the brightness of a bulb, this is fundamentally the power that you're consuming, whereas the length of time that a flashlight will stay lit before it runs out and no longer illuminates is the energy. So in many ways you can think of energy as a duration measure and power as an intensity measure. The ability to scale these independently is something that you can't really do with conventional batteries, lead acid, lithium ion, whatever it is that you're using. The way that they're built, the way that they're structured, is such that if you increase power, you sort of have to increase energy, and vice versa. If you add this extra layer of flexibility that the flow battery does of independently scaling these two, it allows you to really fit a much broader range of applications and gives you more places where you can fit into the market. Interestingly, with this battery as well, we also have lower cost electrolytes than many other flow batteries. And this allows us to, again, get into a broader set of markets than other flow batteries might be able to. Just stepping back briefly, if you want to follow along at home, we should do a little bouncing ball on the bottom here, but our agenda is across the bottom. So right now we're just giving some background, talk about a market screen coming up, and then move into the short-term and long-term markets where we see application, and then finally wrap up. So now that we know a little bit more about the battery technology and how it works, I think the question comes up, how is this unique? And I've addressed a few of these points. One thing that you see is that unlike pumped hydro storage, you don't have the same kind of siting concerns with a flow battery that you do with some of those larger scale compressed air or pumped hydro storage. You also have no carbon emissions in use for this type of battery and extremely fast ramp rates. Your energy, like I said, is independently scalable from your power, and you have a lower cost than some of the other flow batteries because of the low-cost electrolyte on this. These are all unique values to this particular technology. Now, given that understanding of the technology, we need to figure out how this fits in the overall utility market. This is a fairly complicated market, and again, I think we've got an intelligent group here, but just to get everyone speaking the same terms here, I want to talk a little bit about a model of how to think about utilities. Now, at the bottom of this pyramid, the foundation of the utility is what they call operating reserve. And basically what this does is this is 24 by 7 by 365 high availability power. It's always on, always running. This basically keeps the lights on. As you continue to move up the pyramid, you move to progressively shorter durations and higher power requirements. And with that comes a price premium for these markets. This is actually where batteries fit really well as a form of energy storage. You really need to have some type of energy generation down here at the bottom as your operating reserve, be it wind, be it nuclear, be it hydro, whatever it is. That's a generation. Storage fits very well in some of these other markets. We'll continue to talk about the very top of the pyramid in terms of grid reliability. This keeps everything running. This is the frequency regulation that you've heard some of our previous presentations talk about. Now, additionally, you've got the broader time scale, the time shifting application, which includes the renewables integration. That's a bigger market that we'll talk about moving forward. So these are really the two markets that we start with: grid reliability and renewables integration. Now, we've looked at some other markets in addition to these, and they don't make as much sense for this particular battery technology. I don't want to spend too much time on this slide because it's fairly complicated. One thing that's important to notice, however, is that because of the electrolyte that we're using, the bromine, which has some toxicity issues, much like its cousin chlorine, there's some issues around siting this particular battery in a population center or in a commercial area. So that knocks out one of the largest and most interesting markets, which is the retail time of use market. Now, importantly, I do also want to highlight that this is a key area of research for our research team up at Lawrence Berkeley Lab. They're finding ways to complex the bromine in order to mitigate the safety issues of this. But even with technological solutions for this issue, there will continue to be perceptual issues. So we think this actually pushes that renewables the time of use market farther out. More near term, we think, is grid reliability for a couple of reasons. It's a higher premium, and it's a fast response. It demands fast response out of the technology, which the hydrogen-bromine flow battery does. Farther out into the future, we think renewables integration, which is a larger market, is a great application for this particular battery technology. I'm going to put this roadmap up here and let Maria tell you more about how it plays out.
Thanks, Mason. So Mason discussed why grid reliability and renewables integration are the markets that we're going to look at. They fit well with the technology and they have a high value. I'm going to make a specific recommendation, our team's going to make a specific recommendation that the battery be optimized for the grid reliability market first in the next 5 to 10 years, and then move into this renewables integration market later. The reasons for that are a couple. One, like Mason showed you on the pyramid, this grid reliability market is higher premium. You're going to get a higher price for every megawatt hour of power you sell in this market. So as the costs of the battery come down, this is going to be the first market we think it's going to be able to move into. The other reason is that these market sizes, you see this is a $10 billion market. This is a projection as renewables penetration increases. Because renewables penetration is increasing at a certain pace, not instantly, and because co-location with a wind farm depends on a lot of development and the renewables integration market, in the sense that right now wind farms aren't paid for the quality of their power. They need to be paid for the quality of their power before they install a battery on site. We expect this market to expand a little bit later down the line, and so we're recommending that it be moved into later. I do want to point out that this ability to move from a grid reliability application to a renewables integration application is a really unique asset of our battery and a unique value proposition. Like Mason discussed, we can do both power applications and energy applications in the same battery, both longer and shorter timescales, which allows us to capture value from both of these markets at some point down the line, which will make this a much higher value battery. So if grid reliability is the first market that we're going to move into, we're going to spend about the next 4 slides discussing specifically what does this battery need to look like in order to compete in that market. Along the left side of this chart, you have different characteristics of batteries and of storage technologies, and of also natural gas, which is not a storage technology, but is our biggest competitor in this market. Across the top, you have the competitors that we think are going to be the most important players, and what this battery is going to get compared against when a customer decides whether or not to buy it. Ramp rate, it needs to ramp to a full power in seconds. That's easy for our research team to get this battery to do. That's not a big challenge for them, and it's not something they're going to need to spend research time working on. The next 3 lines of this chart are things that the research team is going to need to balance with the cost of the battery and do a little bit of work, but are absolutely within the capabilities of the battery to do. It needs to be about a 15-minute discharge time. This is the standard for grid reliability, frequency regulation, power application. It needs to be a big, high-power battery, about tens to hundreds of megawatts. And it needs to have an efficiency between 70 to 90%. Efficiency is an interesting number. In a flow battery, efficiency is not a characteristic of the battery. It's a characteristic of the operating point that you choose to operate it at. So our research team can build a battery at a different power that can operate at 70%, or 90%, and it's just up to them to do a cost breakdown or a cost optimization where if this battery is cheaper at 70%, they build that battery if it's worth buying the extra energy, and those costs break out. So again, these 3 lines are things that the research team can do, and they just need to make sure that they can do them at the right cost. The last line on this table, the lifetime, is going to be a big challenge for the research team, and it's a big challenge for any kind of battery, and it's something that they really need to think about. A natural gas turbine, which as I said is our biggest competitor, has a 20-year lifetime. In order to compete with a natural gas turbine, the battery has to have a 20-year lifetime, which will be a challenge, and it will be a challenge in testing to prove that it has a 20-year lifetime. So at what cost do these features need to come? I'm going to show you installed costs first, because this is what a lot of people in the storage market like to talk about. Dollars per kilowatt and dollars per kilowatt hour. You can see lead acid looks like the cheapest here. But if you remember on the last slide, it actually has a really short lifetime. So we're going to argue that a much more meaningful metric is a levelized cost. So here on the left-hand side, you have dollars per megawatt hour. If you take each of these technologies, add the installed costs I showed you on the last slide, and also operations and maintenance costs, fuel costs, energy input costs, and divide them by the number of megawatt hours that asset can deliver over its lifetime, you get a levelized cost. Because this lead-acid battery doesn't deliver as many megawatt hours because it doesn't last as long, its levelized cost is higher. And the lowest levelized cost is what I told you is our biggest competitor, the natural gas turbine. It's coming in, the bottom line, about $300 per megawatt hour, and that's ultimately the number that we need to beat in order to compete in the grid reliability market with a natural gas turbine. So I've discussed a lot of the specifics about the grid reliability market. Chris is going to finish that up and then take a step back.
Thanks, Maria. So now that we know the key performance and cost targets that our research team is going to need in moving forward and further developing this battery, the question then becomes of where should they implement the battery to take advantage of the grid reliability market. The question of geography is really important because different regional grids have different rules for grid reliability services. And so what we've done here is compared 4 different regional grids based upon 5 different metrics, and I'm going to save you the detailed comparison of them and pull out the takeaway from this slide, which is that the New York Independent System Operator offers the most favorable marketplace for the short-term rollout of grid reliability, of our technology for grid reliability services. Indeed, because New York has a very aggressive renewable portfolio standard, we see rolling out into the grid reliability market in New York as a good toehold into gaining the further ability to integrate renewables in New York later on. So in the longer term, we're going to look towards the renewables integration market after first gaining a toehold in grid reliability services. Remember, a key value proposition of our technology is that we can independently scale power and energy, which means that not only will we be able to deliver high power, but also through adding storage capacity of reactants at a low marginal cost, we'll be able to expand the energy storage capacities of our technology. So in the long-term future, we see the best place for our battery in order to take advantage of multiple revenue streams to take our technology and place it at a wind farm to allow wind farm operators to both play in the grid reliability markets as well as take some of the power that they generate at night when it's not as highly valued and shift that through storage to deliver it to the grid during peak period hours in the afternoon. We've talked with several wind farm operators, and they do see this as a very optimistic long-term opportunity for them. There are some transaction cost issues to renegotiating their power purchasing agreements in the short term, however, and so we see this as a longer-term market opportunity. Luckily, in order to hit this market, our performance characteristics are largely the same as grid reliability. We're going to need to continue to deliver high-power services in order to smooth out wind intermittency. And in addition, wind farm operators are looking for a long lifetime of guarantee of approximately 20 years. The main technological difference is going to be we're going to have to offer a 4 to 8 hour discharge time. And like I said, we can do that at a low marginal cost through adding more storage tanks. The takeaway here is that in order to take advantage of the renewables integration market, all we're going to have to do is add more storage tanks. And the low cost of doing so sets up this market very, very well after we first hit up the short-term grid reliability market. So those are our two markets, grid reliability first, and then renewables integration second. So what are our scientists going to need to do in order to get to these markets? Well, first of all, they're going to have to keep pace with a very dynamic regulatory and competitive landscape. In our research, we've uncovered approximately 150 pilot projects for grid-scale storage currently. Of course, most of these are still in the planning phase, and some of them are going to drop out as the market changes. But what this indicates is that there's going to be a lot of learning by doing across several different technology types. And this experiential learning, we expect to drive down the costs of all technologies as they partake in the pilot experience. A couple of other patterns drop out from our analysis as well. First of all, we can see that the market is really understanding batteries in terms of life cycle of energy metrics, or lifetime cost of energy metrics. As we can see, the market is shifting away from higher lifetime cost assets, such as lead-acid batteries, and more towards lower lifetime cost assets, such as lithium-ion batteries. Another pattern that emerges from our analysis is that there are a lot of emerging technologies out there. And in addition, there's a lot of companies that are looking to integrate multiple storage technologies in the same application in order to take advantage of different revenue streams. So the takeaway here is that our scientists are going to have to keep their finger on the pulse of this aggressive competitive landscape. We feel that our lead scientist, Venkat Srinivasan, is well capable of doing so. He's an internationally renowned batteries expert, and he also keeps track of the marketplace through his weekly blog, This Week in Batteries. I suggest you all check it out if you have interest and time later on. Another thing that our research team is going to have to keep their eye on is the dynamic regulatory landscape. First of all, there's an effort, I think Jay's group mentioned it earlier on, there's an effort at the national level to converge regional grid reliability service rules. And so what the Federal Energy Regulatory Commission is looking to do is to require regional grids to better value the performance characteristics of batteries and integrate those performance characteristics into their tariff rules and market structures much better over the short-term future. Furthermore, states are looking to gradually ratchet up their renewable portfolio standards. And in addition, a couple of states are looking at integrating storage portfolio standards. There was a law passed here in California in last year that is requiring regulators to undertake a study that might later on require utilities to deliver a certain portion of their delivered electricity directly from storage assets. Furthermore, regions that have experienced high-speed rollouts of wind integration, especially in concentrated geographic areas, are increasingly looking to increase the price of integration for wind farms. So we feel that this evolving regulatory landscape is going to be a tide that lifts all boats in the battery and energy storage marketplace. And eventually, which winners come out ahead is really going to rely upon the lifetime cost assessment of those technologies. So in moving towards commercialization, I'm going to hand it over to Peifu, who's going to take us down the road for what our scientists need to look to further.
Thanks, Chris. So what does this changing environment mean for our technology? Today, our technology is at a rather early stage. The research team expects to spend about 5 years in developing a prototype, and we expect it to take another 3 years or so for the testing and a pilot demonstration and roll out eventually in 2019, towards the end of this decade. There are three key takeaways for successful commercialization. First and foremost, the technology must meet the technical performance criteria we have outlined earlier, or else nothing will work. And at the same time, prove that this is reliable on the grid. Secondly, during the testing and pilot stage, it is best to work with utility partners because they're basically the gatekeeper to the grid. But these people are extremely risk averse. What that means is that they are less willing to adopt new technologies. So we're recommending that our research team to work with corporate partners, such as large wind farm operators, who are more willing to adopt novel technologies. And once the technology is adopted, it'll be easier to convince the utility players to work with our scientists. Earlier, Chris mentioned that there's a dynamically changing environment. If you combine that with a long road to commercialization, you might wonder, is a hydrogen-bromine flow battery still going to be valid down the road in the future when it's ready for the market? Our answer to that is a resounding yes. And this goes back to the point of the unique value proposition of our battery in that it can independently optimize for energy and power so that the scientists can actually adjust the battery features according to the market needs and meet and beat the best technologies out in the market and adjust according to the changing regulatory environment. Ladies and gentlemen, it has indeed been a long day. So for those of you who have dozed out in the past 15 minutes or 20 minutes or so, the good news is it's okay. Because this slide essentially encapsulates the key findings of our team. So we are basically recommending that the scientists start off with the grid reliability market because of the value, the high value for premium they have for power and a low entry barrier. In the long term, they should move into the renewables and integration market to take advantage of the low cost of adding capacity. And also, just to mention that in the future, this market is going to get bigger and more mature compared to today. In terms of location, we think it is best to move to New York because it is the most favorable for storage technologies. We also have observed several regulatory tailwinds, such as unification of storage portfolio standards nationwide and the pricing for premium power. However, having said all that, the scientists do have significant challenges they have to tackle, namely the long lifetime. Maria mentioned that they must meet at least 20 years to be competitive with the gas turbines. And also, as Mason mentioned earlier, the perceived and actual toxicity of the bromine that our technology uses. But we remain extremely confident that our research team has the capability to resolve these challenges and take advantage of this huge market in the future. We would like to thank our research team and their commercial partners for their dedication for using their valuable time and resources to address this global challenge, the grid-scale storage. And we'll be more than happy to take any questions you may have. Thank you.
You talked about bromine. I'm here. Bromine, your other problem is hydrogen. That's not a little angel either. So given the fact that you want to store something like 20, 30 megawatt hours, what size are we talking about here? As far as amount of volume of bromine and hydrogen, how you plan to deal with that?
So that depends a lot on the pressure that you store the hydrogen at, which is a cost number. It also depends on the concentration of the hydrobromic acid, which determines the concentration of the bromine. A very preliminary cost calculation came out to something like 10 cubic meters total. But again, that might, I didn't include costs of how much you would have to pay to store the hydrogen at that kind of pressure. The size, 10 cubic meters total for the tanks. For a 500 kilowatt hour. Sorry, 500 kilowatt hour.
just wanted to follow up on that bromine issue a little bit more. I've worked with hydrogen bromide in the 90s quite a bit, and it's one of the nastiest things I've ever worked with. It corrodes everything in sight. It takes special ways to get rid of it. It's just any other tech. If you put this bromine up with all these other technologies, and I had these pictures of bromine in my head, you really have to address that issue because you're mentioning it briefly, but you're downplaying it a lot, in my opinion, and it's a very serious issue, bromine. To the lab guys, I'd like to point that out as well. It's so nasty. I'm sorry. Yeah.
We absolutely agree. It's absolutely an issue, both the bromine gas, which it's dissolved, but it's also a gas, and the hydrobromic acid. It's an issue for the battery because it breaks down, the acidity breaks down the electrodes in the catalyst. There are a lot of safety regulations that the research team will have to be aware of as they develop the battery. I will say that we use toxic chemicals in a lot of places. We use chlorine and bromine in industry in a lot of places. There are standards for doing it, but
Put big tanks in the ground, big tanks in it. You just don't just store the stuff and use it for processing. Just let a big tank of bromine sit for 20 years. I don't even know how you do it because it would just corrode through everything. But you have to really address that issue. I just want to point that out to the lab guys, especially with that issue.
thanks.
To expound upon his point, there's a company called VMK that the Chinese bought up. I think it's a precedent, and they don't use that bromine, but it's a flow battery, and I'm not sure that technology is something that could be a major competitor to you. Now that it's off the market, the Chinese bought it up. I don't know if we can monitor it.
Interesting. I don't think that we've come across it yet, but we'll definitely keep our eye out for it. Like we said, there's so many different competitive technologies out there. Thank you.
Hi guys. One thing I didn't hear was on kind of the resources side. Do you know how much hydrogen, how much bromine you would need to access, each of these markets? And did you wrap, any of the cost of manufacturing that amount of hydrogen? I don't know what the process is for bromine, but electrolyzing it or however where do you get the hydrogen?
That's not something that we've really looked at. It's a good point, and it's, I think, another point of further research. Other questions? Thank you very much.
Thank you.
Thank you.